Welcome back, everyone. In this video, I'll be going over the lecture for the indefinite integral section. Now, what we're going to do is we're going to start off with what is an indefinite integral? Well, the past few sections, we built up the idea of area between the curve and the x-axis. We've built up the idea of the antiderivative, and then we linked them together by this thing called a definite integral. Well, an indefinite integral is really just going to be notation for finding the antiderivative of f. Okay, so that's really all this is going to do. And the idea is pretty basic. An indefinite integral looks exactly like a definite integral, except there's no numbers on it. So this is an indefinite integral. And that's really the main difference. All this says in words is find the antiderivative of your function f. Now, remember, if you recall last section when I was talking about plugging in when you do the antiderivative, but then you plug in the bounds on the integral. For a definite integral, the c's cancel out. So we really didn't need to include it. Well, since there's no bounds here, you have to use a plus c. And that's a really big deal. So I kind of showed you at the beginning that they really cancel out and they're not actually just not there in the last section, the plus c's. But the plus c for an indefinite integral, it might end up being 0 if you have some way to solve for c. However, it's not going to be, just the same as the last one. You have to actually solve for it. So once again, the idea is just this notation means compute the antiderivative. One thing that it does do for us, which is very important, is that it really gives us notation for saying compute or find the antiderivative. We don't have to say in words, and you can take all those antiderivative formulas that we had before and change them to indefinite integral formulas. And pretty much going forward at this point, we'll rarely say antiderivative. Now I might reference it, but I'll pretty much say compute the integral, because really when people say compute the integral, they mean compute the antiderivative. It means the same thing. All right, so my important note here was really just that the plus c is there, and as we compute indefinite integrals, you will see a plus c. And in general, we call this, this is what we called it back when we talked about just antiderivatives, but if you have a plus c or whatever the letter is, that is called the general indefinite integral. So let's go ahead and just highlight that. So if you do not have information to compute your constant c, then this is called the general indefinite integral, sort of like when we started talking about the antiderivative, we called it the general antiderivative. If you are able to plug in something to compute c, and we saw examples of those before with antiderivatives, this is called the specific indefinite integral. All right, but the idea is just everything in that section is now being replaced with the idea of indefinite integrals. So antiderivative, indefinite integrals, pretty much the same thing. That's the point. All right, so really what we're going to do is just do some more practice with antiderivatives, indefinite integrals, now what we call them, but there's nothing really new in this section. But we will see with a couple word problems in the back half of the section that you can set up indefinite or definite integrals based on your word problem, and that will be important. All right. So number one here, it says evaluate the following indefinite integral and use c for the constant of integration. Right now, if you want, and if you'd like to see, you can put parentheses around this. It's not necessary. So just remind you that everything between the integral sign and the dx, or whatever your letter is here, is going to be inherently inside. So the thing you're computing the indefinite integral of. Well, when we do the indefinite integral, we can do each part. So the power rule says for the first one, we add 1 to the power. 1.5 plus 1 is 2.5, and we divide by 2.5. Minus 11x, and then we add 1 to the power again. We get 3.6 divided by 3.6. And then this is the one where you have to be careful on, because 4 over x, when you have just something over x, we know that's really x to the negative 1 power. So just kind of like simplified on the side here is 4 over x equals 4 times 1 over x or 4 times x to the negative 1 power. And we know that's the special power where it's not the power rule, because when we add 1 to the power anyway, we would get 0, and you can't divide by 0. It is the natural log. So when we do the 4 over x antiderivative or indefinite integral, we have our 4 out front. The antiderivative of x to the negative 1 is the natural log of the absolute value of x. So just wanted to highlight that in a different color just as a reminder. And once again, just like last section, when we did the first problem, I mentioned that when you put the plus c at the very end of all your parts, and we just do that. So plus c. And as far as this one goes, you don't need to simplify it because they gave us kind of strange decimal powers. So we'll just leave it like that. Now, if you have whole numbers especially, you would want to try to simplify, or maybe even fractions. And we could convert this to a fraction, but there's no reason to. It's in the format they gave it to us, and really that's my general rule of thumb, is to leave it in that sort of format. All right, this next one I really wanted to point out just a way you might see a definite or indefinite integral written, and one we haven't seen before. So this, we're just using the letter u, which is not a big deal. The main thing is that we have to integrate du over 1 plus u squared. And if you haven't seen this before, it might trip you up just a little bit, because usually we put the du or the dx or d whatever at the end. Now this means exactly the same thing as 1 over 1 plus u squared du. And that's just because this is a fraction. So if we were to multiply it, we could just multiply the du. We could think about it as du over 1 and multiply it to the top, and then the 1 to the bottom. So it would be exactly that. I'm going to go ahead and just, write it as 1 over 1 plus u squared du. And if that helps you see how to do the problem, you should definitely do that. If you're comfortable just starting from here and knowing that it's really this, you don't have to necessarily write out any of these steps, not even the direct one. But this is actually in exactly a format where you have a formula for already, because this is the derivative of arctan of u. So the integral of 1 over 1 plus u squared is arctan of u. And then we are told to use c for the constant of integration, so plus c. Now a little comment here, especially as we go forward. When we talk about the substitution method in the future section, the common letter is to use u for substitution. And you can use any letter for substitution you want, but whatever letter you start with, I'm just going to mention this now, so when we see it next section, it'll just make sense, because this will sort of look like what next section will look like with the whole u thing, is that you want to end with the letter you start with. Now, since we're not doing any substitution here, there's no risk of ending with a different letter. We started with u's, we just integrated. Now you might, too quickly look at the problem and just not even realize it's u, and maybe think it's x or t or one of our more common letters to use. But you always need to end with the letter you start with. Since we started with u's, we need to end with u's. But as far as this problem goes, that's really it. And once again, I'll just mention again that all the formulas that we had antiderivatives of, since indefinite integrals mean the same exact thing, you have the same formulas. I went ahead and just grabbed the antiderivative formulas that we had before, just to remind you. So pretty much everything over here, when we say function and then we do the antiderivative, really what it's saying is if we integrate this, we get over to this side. And I'll have a formula sheet with all these things with actual integrals, because that's how we want to actually use our notation. I'll have all that written on a separate formula sheet for you, so you can use that for studying or just have as a reference. But I wanted to go ahead and mention that it's exactly these formulas, all the properties, since antiderivative and indefinite integral mean exactly the same thing. It's just going to put notation to it. All right. But really, that's all we have to say about this, because we've been doing antiderivatives, indefinite integrals. Really, we did indefinite integrals when we did definite integrals anyway. There's really just less work. Right? But I just wanted to bring up what I'm talking about in case you haven't watched this video in a while and you kind of forgot exactly where this was. This is in the antiderivatives section. All right, so now that we've done that, one I just wanted to do that's looks a little more challenging, but it's just a reminder, it should come directly from one of the formulas we just looked at. It says evaluate the following indefinite integral, and you see for the concept of integration again, and it looks kind of strange at first because one thing should definitely go off in your head is that we don't have a rule for multiplication. Now we talked about that before. With antiderivatives, we have rules for addition and subtraction. We can bring out numbers, so just constants, but we do not have a rule for multiplication. Well, because we don't have a rule for multiplication, what should go off in your head is that we should actually distribute, or I mean, this isn't a FOIL one, so straight up, we should just distribute the secant of W through, because we got to get rid of that multiplication. And when we do that to the front, we get 2 secant squared of W. And then when we distribute it to the back, we get minus 3 tangent of W times secant of W. Now, as you write this, make sure you include your dw, don't forget that. But we know how to do the antiderivatives of these exactly. We expect that because really that's all we have at this point. We don't have any kind of special rules to integrate yet. All right, and the thing is that the antiderivative, or the indefinite integral of secant squared of W, that is tangent of W. And that's just because the derivative of tangent is secant squared, but you can look at that antiderivative formula sheet or the integral formula sheet I have attached. And we have the 2 out front, and then this is just tangent of W. And then what about the antiderivative or integral of tangent of W times secant of W? That's just secant of W. So we got the minus 3 in front, and then secant of W. And remember all these rules come from the derivative rules, so if it helps to realize it, especially when we're still kind of new to integration, what is the derivative of secant? Oh, it's secant times tangent. That's perfect. That's what we should have. And then when we integrated each part, which we've done both parts now, we get our plus C. All right, but as far as indefinite integrals, once again, we're just using those same formulas. We're just putting new notation to it. So just remember the formulas we have and we've been using, and really this section is not anything new at this point, at least. So the second part of this section, and it's kind of quick as well because we've done some types of word problems in a previous section, but we want to know when we have word problems, we know we should integrate if we're given like the rate of change or the velocity, and we want to get back to the original because that's what the antiderivative does. But in some problems, you want to do a definite, and some problems you want to do an indefinite integral. So the important thing is knowing which one you want to do and then actually setting it up to do that. All right, so really what I'll do is one of these problems will be a definite, one of them will be an indefinite integral, and we'll see the difference, and hopefully you can realize that. So when you set up your own problems, you can do it correctly, because you could do either one with definite or either one with indefinite integrals, but it's going to be a lot more challenging if you do it the wrong way with one of them, because you're going to have extra work to do. All right, so number 1 here says water flows from the bottom of a storage tank at a rate of 400 minus 8t liters per minute, where t is between 0 and 50. So the reason where they come up with this, if you're unsure, is that at t equals 50 is when this rate is 0, and the rate of water flowing out, we don't want to be 0 because that means it's actually flowing in if it's negative. Right, and it says find the amount of water that flows from the tank during the first 30 minutes. Well, one of the big things here is that we're given the rate. This is like its derivative, and we want to find the amount of water, which is the original. So just to break this down in words, we have the rate of change, and we want the amount of water flowing that flows out, and then we want the amount that flows out during the first 30 minutes. But the way we can kind of word this sort of like in this inequality notation is 0 is less than or equal to t is less than or equal to 30. Right, and just to highlight this even more, this is what we're given. We're given the derivative in general terms, and we want the original. Well, what do we want to actually know about the original? Let's pretend that f of t is the amount of water at time t. Well, then what is f of 30 minus f of 0 representing? In words, this is the amount of water at time 30 minus the amount of water at time 0. Well, if water is flowing out, then what's happening is the amount of water at time 30 minus the amount of water at time 0. It'll tell you how much actually left. And that should make sense. So if you have, let's say we had, for example, keep in mind this is the amount of water that's flowing out. So our numbers here might not make a lot of sense at first. But let's say that the amount of water at time 30 is like 700. I'm just throwing out a random number, and the amount of water at time 0 is 100. Then the amount of water that's flowing out throughout this process is 700 minus 600, or sorry, 700 minus 100, which is 600. Now, I'm just making these numbers up, but the idea is that if we can figure out the amount of water at time 30, the amount of water at time 0, and subtract them, then we will get the amount of water that is flown out. All right, well, if you think about what we're given here, we're given the derivative and we want to find out the original. So in complete general terms, we are given f prime of x, and we want f of 30 minus f of 0. Well, the fundamental theorem of calculus part 2 says that the antiderivative of from 0 to 30, or integral from 0 to 30 of f prime of x dx equals f of 30 minus f of 0. So what we're going to do is we're going to use our derivative, which is this formula here. We're going to integrate it from 0 to 30, and it's going to give us back exactly what we want. So if we just set up that definite integral for this one, it'll give us the problem's answer. That's exactly what we want. And one thing you can kind of think of as far as why we're doing a definite integral is you're trying to figure out what is happening over an interval of time. We're trying to figure out what is happening during the first 30 minutes. The main difference between a definite and indefinite integral, as you'll see, is when you do an indefinite integral, you want to figure out something that's happening at a specific time. A definite integral is trying to figure out something that's happening over an interval of time. All right, but all we have to do is exactly this. We take our derivative formula, which is 400 minus 8t. So let's just say amount of water flowing out for the first 30 minutes, but I'll not write the rest of that. We integrate from 0 to 30. We integrate the derivative, which is 400 minus 8t dt, because that's our letter. And you just set up and solve this antiderivative as a definite integral, and you're good to go. And because it is a definite integral, we know we don't need the plus c, we just need to integrate, plug in the endpoints, and simplify. Right, so the antiderivative of 400 minus 80t, or 8t, is 400t minus, it would be 8t squared over 2, which is 4t squared, because 8 over 2 is 4. And we want to evaluate from 0 to 30. We do not care to add in the plus c because it's a definite integral. And so we plug in t equals 30, subtract. We plug in t equals 0. And for t equals 30, we got 400 times 30 minus 4 times 30 squared. And then when we plug in t equals 0, you can actually visibly plug it in, but we should see that it's going to be 0 because it's just all powers of t. So we get 0. And now if we go ahead and just plug this in our calculator, since the numbers are kind of big, get a quick answer here, we'll be done. Let's go ahead and grab that. And we got 400 times 30 minus 4 times 30 squared is 8,400. So we got 8,400, and the units of the water here are liters, because remember when we do the antiderivative, we're really multiplying the units here times the time because of the dt. So it's just liters. That much water has flowed out from the tank in the first 30 minutes. If you wanted to do like from 10 to 20 minutes, just that interval, you would just set up the integral from 10 to 20. If you wanted to do the last 30 minutes, well, it stops at 50, so you'd integrate 20 to 50. But once you realize that if you're doing it over an interval of time, you just set up a definite integral, and then you are done once you do it. So the next one you'll kind of guess here would be an example of using an indefinite integral for a problem. And it says the following. A bacteria population is 3,000 at time t equals 0. So that's probably going to be important. And its rate of growth. All right, so its derivative, because it's the rate of growth, is 1,000 times 7 to the t bacteria per hour after t hours. What is the population after 1 hour? Well, the reason why this is going to be set up as an indefinite integral is we want just something happening at a certain point. So let's pretend that P of t equals the population at time t. So just giving a name to reference. What we want is we want P of 1, because the rate of growth here is the bacteria per hour after t hours. So when we integrate it, the time interval still represents the same thing. It's still telling us the amount after so many hours. So we just want P of 1. We don't want P of 1 minus P of 0, because what happens is if we did P of 1 minus P of 0, we would be answering how much population was added during the first hour. All right, well, since we have the derivative, which is 1,000 minus, or I guess I'm all over the place, 1,000 times 7 to the t power, the derivative. And we want to get back the original function. P of t would be the integral, or the indefinite integral specifically, of the derivative 1,000 times 7 to the t dt. And now we go ahead and plug this in. And if you want to go ahead and plug it in, or sorry, not plug it in, integrate it. If you want to go ahead and integrate it, you might not remember the antiderivative or integral of 7 to the t power. So I'll just remind you that it is 7 to the t power divided by the natural log of the base, which is 7. And then because we're doing an indefinite integral, we have a plus c. All right, so we got a formula for P of t, and I'm just going to write it more specifically. So P of t equals this. So I'm not going to have the intermediate step. I'm going to write it 1,000 over the natural log of 7 times 7 to the t, just because this is a number. So I like to have my just numbers in front, plus c. Well, we need to figure out P of 1, but in order to do that, you need what c is, because if we plug in t equals 1, that's great. But we don't have what c is, we're not going to get an actual number to round. And that's when this comes into play. This says P of 0, because it's at time 0, equals 3,000. And we use this to solve for c. We got P of 0. Well, we plug in t equals 0 here. 1,000 over the natural log of 7 times 7 to the t power plus c. And that must equal 3,000. Right, well, we want to go ahead and plug in t equals 0, so I'm going to replace that with 0. And this is why it's so important not to just involuntarily cross out or say when you plug in 0, you get 0. It's because 7 to the 0 is 1. So this is 1,000 over the natural log of 7 times 1. We'll get rid of that, plus c equals 3,000. And then you can subtract this number off, 1,000 over the natural log of 7 to each side, and you get c equals 3,000 minus 1,000 over the natural log of 7. Now make sure as you are working through this problem, you want to round at the end, but you don't want to round now. This would be a bad idea to type this in your calculator and round. Just leave it alone. And what we're going to do is go ahead and plug this in. So now we know c is, we go ahead and just write the first part. We have 1,000 over the natural log of 7 times 7 to the t. And when we plug in c, we get plus 3,000 minus 1,000 over the natural log of 7. Now you can do some rearranging here to sort of simplify. You can definitely factor out 1,000 because everything has 1,000. You can find a common denominator and factor out the natural log of 7 on the bottom. But in my opinion, it's not worth it because all we want to do with this is, now that we have p of t, we want to plug in 1. So now we just take this formula for p of t and we plug in t equals 1. So p of 1 equals 1,000 over the natural log of 7 times 7 to the 1 power plus 3,000 minus 1,000 over the natural log of 7. Now for this one, it might help a little bit just to simplify because you do have 7 of these 1,000s over the natural log of 7 minus 1 of them, which would leave you with 6. And you can do that, a little bit of simplification before you plug in the calculator. So 7 minus 1 is 6. We would have 6 times the 1,000 over the natural log of 7, and then plus 3,000. But you still have to type it in the calculator anyway, and at this point I wouldn't try to do anything extra. Let's go ahead and grab that. And just to make it a little easier, I'll write it as 6,000 for the top over the natural log of 7 plus 3,000, and we get 6,083. So 6,083 is the population. All right, so what that's saying is after the first hour, we a little more than doubled the population. But you can actually go through and even by plugging in t equals 2, you'll see that it grows significantly more because what happens is you actually have 48 of these because this would be 7 squared. So if this number maybe doesn't make sense because you think, oh, well, it should grow like, by 7,000 or something because we would have 1,000 times 7. Well, if you plug in 2, this would be 48, and you can see that it actually grows like 9 times from the original. So that's how exponential things work anyway. But the point here is that noticing the difference in the word problems. We had to figure out something over an interval of time. We use a definite interval. We have to figure out something at a specific time. We set up an indefinite interval. And that's a very, very important feature. But that is this section, and I'll see you in the next one.